if we just add water, are we changing the number of moles? No, because if we look, here's a little example. The number of moles remains the same, so the mole stays the same. If we look here, we have 2 moles. If we add 1 liter of water, we still have just 2 moles. And the only thing that has changed is our volume. So when you're doing a calculation with this is always pretty easy. You just figure out how many moles you have, and then you divide by your final volume, and that's it. Okay, so figure out your number of moles, divide by your final volume. So I would say, okay, if I was doing this one, I could do it just by looking in the beaker. How many moles do I have? I have 2 moles. So how many do I have later? I will still have 2 moles. And to find my new concentration, I just divide by my new volume because it's moles per liter. Okay? So we have a little example here. Find the moles, divide by the new larger volume. And in fact, I'm just going to put that down there and solve it over there. If we have 2 liters, and I'd like to draw your attention to the word of, because of has a mathematical meaning. Does anyone know what of means in math? Means multiply. It means times. Okay? So in other words, you're going to multiply. So when it says 2 liters of a 9 molar solution, that actually gives you a clue of what the first thing you are going to do in this question is. You are going to take 2 liters times 9 molar. Yeah? So let's see what it looks like when we do that. 2 liters times, and you don't have to write this down because it's just down below, times 9 molar, which is 9 moles per liter, right? That is 9 molar. What happens to our liters when we do that calculation? They get canceled out, and what are we left with? Moles. So if you're finding moles, if you have 2 liters of a solution, then you just do your calculation there, and we get 18 moles. So that's how many moles I had in my original solution. And now it says it is diluted to a final volume of 6 liters. So our new concentration of the NaCl, concentration is always found by taking the moles and dividing by the liters. And so we get 18 moles, and our new volume is 6 liters, so we end up with 3 moles per liter. Do you remember doing this last year? A little bit? Okay, good. So that's the first type of dilution problem you might come across. There is another type of dilution problem you could come across, and that is, and in fact, I have been doing this, and Chris O has been helping me because he's my peer tutor in one of my blocks, doing some dilutions to make some new solutions. Because we had some 0.4 molar iron nitrate, but the lab we're going to be doing requires 0.2 molar. So we have 0.4, but we want to get 0.2. So we're going to have to dilute it to make it less concentrated. And that's what this is about. You're preparing a diluted solution from a more concentrated stock solution. So you're going to find the moles that you need. How much do I need in my diluted solution? And then, once you know the moles that you need, you can figure out the volume of the stock solution, and this is going to involve a unit conversion. This is just a unit conversion. So for example, if we want to make 2 liters of, and again, we're just going to be measuring these little particles, little dots. I want to make 2 liters of 2 molar solution. That's what I want to make. What does the word of mean? Of means multiplication. It means times. Okay, so that's going to be times. And I want to do that by diluting a more concentrated solution. So I want 2 molar, but I'm starting with something which is more concentrated than that, 8 molar. So in terms of the math, what I'm going to do is I'm going to say, well, what do I want? What do I need in terms of moles? That's going to be here. This is what I need in terms of moles. So my moles of dots is equal to 2 liters times 2 moles per liter, because it's 2 liters times of 2 molar, 2 moles per liter. And that gives me 4 moles. Second thing I want to know is how much of my 8 molar am I going to need to contain that 4 moles? Okay, so I want to know how much volume of the 8 molar. No. You're just somebody weird. Yeah, that's just random. Nope. There we go. Okay. All right, so we have, we wanted to know how many liters of the 8 molar we need. And we know we need it to contain 4 moles. What do we need to multiply by in order to get liters? We're starting with moles. Liters over moles, yes. Okay, so we need to have liters on the top and moles on the bottom. Don't forget, what does capital M mean? Moles over liters. So what we have is we have 8 moles per liter. So we would write 8 moles per liter. Okay, we just flipped it upside down, okay? And so we would end up with then 4 divided by 8 is 0.5 liters. So what I will then do is I will measure out 0.5 liters of my stock solution, and then I would dilute it to a final volume of 2 liters. So I would have 0.5 liters, and then I would add another 1.5 liters, and I would end up with my new, more dilute solution. If you want to take a look at what that would look like, you know, sort of with those little dots, I'm not actually sure that this is helpful, but we're going to take a look at it, and you can let me know if it's helpful at all. This is what we want. Yes? We want to have 2 liters. So you can see each of these little divided boxes is 1 liter. So we have 1 liter up here, and we have 1 liter down here for a total of 2 liters. And we want our solution to be 2 moles per liter. So in each one of those liters, we need to have 2 moles. And if we're just looking at the picture, we can say, how many moles do I need in this solution? Well, obviously I need 4 moles, yes? And that was where we did this math to figure out how many moles. Now we're figuring out how much of the stock solution do we need. Well, if I draw out the stock solution, if this quantity here, if this whole thing is 1 liter, yes, there are 8 moles per liter, 1, 2, 3, 4, 5, 6, 7, 8. If I was to use 1 liter, I would have too many of the dots, yes? So I'm just going to use a half a liter, and that will give me the 4 moles that I'm going to need in order to make that solution. Okay? Was that at all helpful? A little bit? Okay. So I'm going to leave it in my notes. I won't take it out, but if it didn't help you, that's okay. You can just do it via math. Okay? So if you found that confusing or anything, you can just ignore it. All right. So basically, if you are doing a dilution calculation, there are 2 ways that you can do it. You can either find the moles. Step 1 is always going to be to find the moles. And then depending on what you are asked for, you might be asked to find the liters, in which case you'll take those moles and you'll multiply by liters per mole, and that will leave you with liters. Or you will be asked to find the molarity, which is moles divided by liters, so you will take those moles and divide by whatever your final new volume is. Okay? So that's method 1 of doing these problems. And anytime I forget how to do a dilution, I personally always end up going back to this method because I can always find moles. And then because I'm good with conversion factors, because I've done this for a long, long time, I can go on and do the second step. You may or may not like this, right? Because you don't have 30 years of doing conversion factors. So you might prefer the second method that we have, which is also a good method, is the dilution formula. M1V1 equals M2V2. How many of you have seen something like that before? Okay, yeah. So if you have seen this before, that's great. M1 and V1 go together, yes? So they would be joined by the word of, usually. And I know I wrote here that it is the initial concentration, but it doesn't really matter. You could make M1 and V1 your final volume and concentration. M2 and V2 will also be joined by of, usually joined by of. Usually, usually joined by of. If you care why this formula works, pay attention for the next couple minutes. If you don't care why the formula works, close your eyes and have a little rest, okay? Because the formula will work whether you understand why it works or not, okay? M times V, that means we have our molarity times our volume. Molarity is, of course, moles per liter. And volume is measured in liters. So M times V is moles, yes? And what do we know about the moles before dilution and the moles after dilution? They are the same. So the moles before are the same as the moles after, and because moles is equal to MV, M1V1, moles number 1, has to be equal to M2V2, which is moles number 2. That's why that formula works. Okay? We're going to do a few examples. If you feel like you're ready to go and you would like to just work on the questions at this point, you could just do the odd questions. Don't feel obliged to do them all. Do the odd ones, and then if there's a section you feel you need more work on, you could do the extra ones. But I'm going to go through a couple of examples showing both the mole method and the M1V1 method. If 45 milliliters of water is added to 250 milliliters of a 0.75 molar K2SO4 solution, what will be the molarity of the diluted solution? So first of all, are there any volumes and molarities in there that are connected? Yeah, these two are connected. And the ones that are connected we can use to find moles. So using our mole method, the moles of K2SO4 is going to be equal to, if we are using volume and molarity, should I be using milliliters in my calculation? No, I should be using liters. So I'm going to say 0.250 liters. And if I want to find moles, what unit has to go on the bottom? Liters. And what unit has to go on the top? Moles. And so I don't have to flip it this time. I can just use 0.75, and remember that is moles per liter. So it is 0.75 moles per liter. And we get, oh, I do have a calculator here, that's good. 0.25 times 0.75, and we get 0.1875. In the mole method, once you have the number of moles, you say to yourself, what is the question looking for? Yes? Pardon me? Significant figures will matter, but I won't bother with them until the very end. Yes? Especially because it will prevent me from having any rounding errors. Yeah? So what are we looking for in this question? Molarity. So we want the concentration of K2SO4, and we want it after it has been diluted. So I'm going to write a little DIL down at the bottom to indicate that it has been diluted. And if we're looking for concentration, how do we calculate a concentration? Just moles over liters. So we're going to take our moles, 0.1875 moles, and we will divide by, I'm going to give you three choices of what we're going to divide by. A, 45 milliliters, B, 250 milliliters, or C, 295 milliliters. So read the question carefully to yourself or to your partner. Okay, shall we vote? And you can always vote for I don't know with the little I, A, B, C, D, go. Yeah, so it does actually end up being 295, and that's because we have taken 45 milliliters of water and added it to the 250. So this down here is going to be our final volume. And so the final volume is 45 milliliters plus 95, no, not 95, 250, which is 295 milliliters. So down on the bottom, we will write 0.295 liters. And we get 0.636. And now we're going to look back at our sig figs. What's the smallest number of sig figs we've worked with in this question? Yeah, we got a 2 here, yes? We got 2 sig figs right there. So this is going to round then to 2 sig figs, 0.63 molar. 4, that's what I meant. 0.64 molar, yeah, we round up, yeah, thank you. Or you can use the M1, V1, M2, V2 method. The only thing I will caution about this one is that it is easy to put the wrong M in the wrong place or the wrong V in the wrong place. So before you do this method, I'm going to make you, so if you use this method to show your work, you will be given credit for writing M1 equals and writing the value, M2 equals and writing the value, V1 equals writing the value, and V2 equals and writing the value. That will just keep you from messing up what goes in where. Yes? I'm going to erase all my stuff up here. Going back to the question, M1 and V1, those have to be connected quantities, yes? So, M1 and V1, are there any 2 connected quantities in that question? Yeah, we have 250 milliliters of 0.75 molar. So V1 is going to be 250 milliliters, and M1 is 0.75 milliliters. M2 and V2 will also be connected, but one of them is going to be missing because we need to have one variable that is unknown. Do we know M2 or do we know V2? We know V2, and how much is V2? 295 milliliters, and M2 is we don't know how much molar. And somehow or other, watch out, over in M1, I wrote 0.75 milliliters. That should have been 0.75 molar. One of the nice things about this formula is it allows you to not have to change liters into, or sorry, milliliters into liters. Because you've got a milli and a milli, they will cancel out. Okay? Do you guys like solving your equation first and then plugging in, or do you like plugging in and then solving? Solving then plugging in, excellent. All right, so let's do it that way. So we are going to be looking for M2. So if we have M1 V1 equals M2 V2, if I get M2 all by itself, and I've brought it over onto the left, I've just sort of flipped my equation over because that's going to make it easier to write a string. Okay, I'm going to have M1 V1 over V2. And this is why I like to have done this, is because now I go, what's my M1? I can just see it right here. I'm not wondering what volume to use or what molarity to use. So that's 0.75 molar. You do have to use units here. Volume is V1 is 250 milliliters, and V2 is 295 milliliters. Do you see how the milli and the milli here cancel each other out? Yes. It's totally fine. You want to convert it to liters, totally good, not a problem. As long as you're consistent. You can't have one in milliliters and one in liters. That would be bad. Okay, but yeah, either way is good. So those will cancel out, and the only unit we're going to be left with is molar, and lo and behold, we do that calculation, we get 0.64 molar, which, yay, is the same. It should be. You're really just doing exactly the same math, you're just presenting it in a different way. Okay? Would we like to do another example? Yes. You get to pick. And in fact, when we get into KSP, I'm going to show you a third way as well. But for this one, I think these are mostly the methods that you've learned in grade 11. So I'll introduce the new method, but you're not obliged to use it. You can stick with one of these if you want to, or use the new one. Okay? Yeah. So pick a method, whatever works best for you. Oh, I did want to, so if you've been working ahead, you might want to just pay attention for this. This is the procedure for making a diluted solution. So what would this actually look like? Well, here is my concentrated stock solution. Okay? And I'm going to measure out a small amount, whatever I've calculated. Okay? And then we are going to put that into another container. What do we call this particular type of container? Starts with V. It is a volumetric flask. And then we are going to dilute it but when you get really, really close, you can just pour the water in with a beaker, but when you get really, really close to that line, you should switch over to using either a wash bottle, because it'll go drip, 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 or you can use a medicine dropper, drip, 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 because that way you won't accidentally go over the fill line. If you go over the fill line, you are out of luck and you need to start all over again, which would probably make you and I both very sad, okay? At the end, you are going to put a cap on it. You are going to stopper the flask. So that's like a lid. And invert, which is basically turn it upside down and right side up to mix. There is one last thing that you need to take into consideration if you are working with a concentrated acid. And I will be doing some dilutions. You won't be doing this year. I will be doing some dilutions with a concentrated acid. If you have a concentrated acid and you mix it with water, it actually is very exothermic, that whole mixing process. So it can actually cause the glass, because it changes temperature too quickly, it can cause the glass of the container to crack. And what do you have? You have acid going, concentrated acid going everywhere. And that's a bad thing, yes? They also say that it might cause the water to boil and splash out. I actually did watch some YouTube videos of this guy trying to make that happen, and he was not successful. He's like, I don't think this is a thing. So I think the issue is not so much that it boils and splashes out, but that quick change in heat can crack the container, the beaker. We can alleviate this problem by, instead of having the acid and putting water in, which means that the acid is very, very concentrated and we are gradually diluting it, we can put the water in first and then gradually add the acid. That means at no point is the acid going to be super concentrated because it's continually being diluted by that large volume of water that you already have. Yes? Also, water is a really good, it's got a really big heat capacity, which means it can absorb a lot of heat without raising too much in temperature. So that also helps alleviate that effect. You don't need to understand it or anything like that, but you should remember, do as you oughter, add acid to water. And if you're like, why otter? Because you're like, that doesn't sound like anything. It's because it's like otter, like oughta, okay? Which, if you're like, what's oughta? It means ought to. And if you're like, what's ought to? It means should. Do as you should, add acid to water, but that doesn't sound cute. And we can't have a cute little otter floating around with his little flask and his goggles, right? And if you say it with a New York accent, it actually sounds like that. Do as you oughta, add acid to water. Do as you oughta, add acid to water. Good thing I'm not from New York, eh? Okay. If there's anyone who has relatives in New York and you're like, that's a terrible New York accent, I apologize deeply from the bottom of my heart. Okay. Would we like a second example before you turn yourself loose on these questions? Or do you feel like you just want to get going? Ready to get going? Okay. So what you can do is, at this point, you can go and there's also some information on mixing two chemicals of the same solution. Again, I think it'll be just better if you get some practice in, and we can go over this next day if you run into difficulties on it, okay? So just go ahead and do the odd numbers. Okay? Just go ahead and do the odd numbers. And if you get stuck anywhere, call me over and I will help you out.